Here we are analyzing somebody holding an object. The arm is nearly fully extended and the arm's almost horizontal. And we're going to model the forearm as a horizontal piece here, like a rod, like we've been analyzing in the past. And so we have the force of gravity of the milk acting not at the end, but somewhere close. It's 2 kilograms times 9.8 meters per second squared. And then we've got the bicep force, which is located 8 centimeters from the elbow joint. And so we're going to label that on here, right about there. So that's the bicep force. And we see that that's a 75-degree angle. Let's see. The forearm itself has a mass of 2.5 kilograms. We'll put that right. Let's see. The center of gravity is 15 centimeters from the elbow joint. So we'll just put it at somewhere maybe right there. That's 2.5 kilograms times 9.8 meters per second squared. And so that's 15 centimeters. We know that this distance here is 8 centimeters from there out to where the bicep is attached. And we also see over here that the distance from where the bicep is attached to where the milk is 25 centimeters. And so that means it's 33 centimeters from the elbow joint out to where the milk is acting. And so the elbow joint is going to be our axis of rotation. So right here, there's the two bones. There's the end of that bone and the end of that bone going that way. So right there is going to be our axis of rotation. So there, axis of rotation. But at that joint, there are forces. So we have an R sub x and an R sub y. And that's one of the things we're supposed to find here. We're going to find the bicep force right here, but we're also going to find the force at the elbow joint, the magnitude and direction. And so eventually we're going to take this R sub x and R sub y, combine them into a single force R, and find the angle at which that force acts. Let's go ahead and see how we're going to solve this problem. We've got it set up. So we've done most of the hard work by this point. And so we define positive x, positive y, positive direction for torque. We've already decided that our axis of rotation will be right at the elbow. That's nice because then both R sub x and R sub y create zero torque relative to that point. So we sum our torque, set it equal to I alpha. This is an equilibrium problem, so alpha is 0. We see that the weight of the milk, 2 kilograms times 9.8 meters per second squared times 33 centimeters. We see that torque is clockwise. It's going to, if it were allowed to rotate, the arm would rotate clockwise due to that force. Same thing for the weight of the arm, the weight of the forearm. So 2.5 kilograms times 9.8. Make sure it's force times distance. And that's 15 centimeters from our axis of rotation. And then the only other force that's able to create torque relative to the elbow joint is the bicep force, and that is 8 centimeters away. And of course we should have had sine of 90 degrees here, sine of 90 degrees here, but since that's 1, it's okay not to include that. But here we've got the sine of not 75 degrees, sine of 15 degrees, because it's the angle between this R vector here and the force, and that angle in there is 15 degrees. We say that's equal to 0, and then we can go ahead and solve. And you might be wondering, do I need to convert these into meters? I've got 33 centimeters, 15 centimeters here, and 8 centimeters here. And I'll leave that to you to do the algebra, work through, keep your units throughout, and solve for F sub B, the bicep force, and you tell me if you think that that needs to be that all those distances need to be converted to meters or not. You can leave that in the comments. And so this bicep force comes out to be 490 newtons. And that's one of the things that we were supposed to find. To find our other unknowns, we can sum forces in the x direction. So we see 490 newtons times the cosine of 15 degrees minus Rx equals 0. So we can go ahead and compute that, and Rx comes out to be 473.2 newtons. And we can find R sub y. Oh, we're going to find R sub y, but we're going to sum the forces in the y direction. Set that equal to m times a sub y. Of course, a sub y is 0, just like a sub x is 0. This is an equilibrium problem. So we get R y plus the bicep force, 490 newtons, times the sine of 15 degrees, or the cosine of 75 degrees, minus 2 kilograms times 9.8 meters per second squared, minus 2.5 kilograms times 9.8 meters per second squared, equals 0. And then R sub y actually comes out to negative 82.7 newtons. And that negative sign means we drew R sub y incorrectly. I mean, it could mean that we made an algebraic mistake, but in this case, I've checked the algebra, and it means that we drew R sub y the wrong way. We thought R sub y was going to be up, but R sub y is actually acting downward. So R sub y is downward 82.7 degrees, and R sub x is much bigger. It's 473.2 newtons, and this 82.7 newtons. And so then we're going to find R, and R comes out to be 480 newtons, and this angle right here, 9.77 degrees. And so that, well, 480 newtons, 4.77 degrees below horizontal. And that's the answer to what is the force at the elbow joint. That's right there.